Hi everyone. In this particular video, we're going to be taking a look at the newer addressing scheme, which is called IPv6. This is an addressing scheme that gives us unlimited number of addresses that are available for us to deploy to the different devices that are connecting to the internet. It basically overcomes the limitations of IPv4 addressing that we have. We'll take a look at how to do it. In this particular video, we're going to take a look at an overview of why we need IPv6 addressing. What are the differences in between IPv4 and IPv6 addresses? One of the things about IPv6 is that it's written in the hexadecimal format. So you need to understand how that can be converted into both binary as well as decimal, which is a very important fundamental thing that you need to know about to be able to better understand how IPv6 addresses are configured or the way they're communicating. The last thing that we'll take a look at is how do we write the IPv6 address and what are the different ways that you can make it easier on yourself to write those addresses. All right, let's get into it then. Why do I need IPv6 addresses? You need to understand when IPv4, or in those days just IP, was written, the developers never thought that it would expand to what it has in today's day and age, in which every single device is trying to connect up to the internet. It's not just the PCs, it's not just the servers, it's also your handheld smartphones, it's your Internet of Everything or Internet of Things, which is basically your appliances, your TVs, your Alexas, all connecting to the internet. All of them require a individual unique identifier, the IP address. So as the network, the internet has grown phenomenally, we need to have the ability to identify each and every device on the internet uniquely. And that's where IPv6 addressing plays a big part. With IPv4 addressing, you had a 32-bit address space. Even with that 32-bit address space, because there was no special planning done, because it was never meant for this large of a network, you have a lot of wastage of addresses that has happened. So you don't have full flexibility of of address assignments with IPv4. I'll give you an example of that. They've taken an entire Class A address and use that as a loopback, which is the 127.0.0.0 network that's completely wasted for identifying the local device. So those type of things have been done with IPv4, which limits the number of addresses that you have with IPv4. And that's where IPv6 comes in and solves the issue. By giving a much larger space of addressing that is available to you. So for example, with IPv4, as I said, it's a 32-bit address space. IPv6 gives you 128-bit address space. You might say, well, it's only 4 times bigger. No, that's not the case. When you do look at these addressing in terms of the numbers that are available, this number, even if I had all the address space available, it's 2 to the power of 32. When you multiply it or double it by 2, so basically 232 times 2 to the power of 32 times 2, which becomes 2 to the power of 33. So just by doing a single extra bit, you've doubled the address space. Now you double it again, it becomes 2 to the power of 34, which is quadrupled already from IPv4. And you keep on quadrupling, or you keep on doubling it until you get 128 bits is when you arrive at the IPv6 address space. So a lot of addresses are available for you to be able to assign to different devices, which has now become more of a necessity on the current IPv4 internet, or the internet, which is predominantly based on IPv4. And that's where IPv6 comes into the picture. Now, to take a look at it, first things that we'll take a look at is what you know already about IPv4 addresses and how does that compare with IPv6. Let's take a look at that. The first thing we already discussed is the address space. The size of an IPv4 address is 32 bits. IPv6 addresses are based on 128 bits. So again, it's a huge advantage in terms of the space. And that's one of the biggest differences in IPv4 versus IPv6. That's why I want to go to IPv6, is the bigger address space that is at my disposal to assign addresses to all these different addresses or different devices connecting to the internet. Now, in terms of the inner workings of it, the way you write it, if you guys remember the IPv4 address, you wrote it using a decimal number. So for example, you had the first octet, which was limited to 1 through, let's say, 223. Let's put 151 over there. This is a decimal number. 5, it's a decimal number. So the numbers that you have available over here are all between 0 through 9. It's a decimal numbering scheme. With IP addressing, with IPv6, you don't write it in decimal, you write it in hexadecimal. Hexadecimal, the numbering scheme is based on 16 different digits that you can have. So the normal 10, 0 through 9, which is 10 digits, plus they have another 6 extra digits, which are called hex digits, which are represented by alphabets. A, B, C, D, E, and F. These are the 6 extra digits besides the normal 0 through 9 that can be written to represent a hexadecimal digit. And that's what is used in IPv6. We'll take a look at a detailed look at how do I write the same number in decimal versus how do I write it in hexadecimal. I'll also show you the binary equivalent of the same so you guys have a better understanding of it. When you go into details about the IPv6 address, you have the ability to break that hexadecimal digit into binary. Very important information for you to understand how IPv6 addresses are written. The other thing, we just softly alluded to it in terms of the written notation. When I wrote it, I wrote a decimal number over here, separated with a dot, decimal number, separated with a dot, decimal number, separated with a dot, another decimal number. So it's a 4 decimal number, 4 octets, 8 bits, separated with dots in the middle. That's what an IPv4 address looks like. An IPv6 address that you have is basically represented as a hexadecimal. Now, hexadecimal, 4 bits equates to 1 hex digit. So if I have the IPv6 address as a 128-bit address and you divide them by 4 bits because each hex digit is 4 bits, you get 32 hex digits. So although it's a 128-bit address, the way it's written is in hexadecimal format, and 32 hexadecimal formats gives you the 128 bits. So when you see an H over here, which is in my case representing a hex digit, that H over here represents 4 bits. And I'll have 32 of them giving me the 128-bit address. Now, the way it's written is you write 4 of those hex digits in one block, and after the block you separate the different blocks by using a colon in the middle. So the delimiting character, which was a dot in IPv4, is a colon in IPv6. Again, you're going to write another 4 in a block, 4 hex digits, separated with a colon over here. So and keep on writing it. So in each block you have 4 hex digits. So if you do the math over here, so block contains what? 4 hex digits. So rather than delimiting with the dot, they use a colon over here. If I have 4 hex digits and each hex digit is 4 bits, so this gives you 16 bits in this block. So you'll have 16 times 8, which is a total of 16 times 8, which is giving you the 16 times 8 gives you the 128 bits. So each block has 16 bits. All right? So this is what an IPv6 address will look like. Basically 32 hex digits split into blocks of 4. Like that. So you're going to have 8 blocks. Like that. Now, this is what it looks like. Now, how do you break it down between your network portion and the host portion? This is where the differences come in. Big differences in the sense of the way IPv6 addresses are constructed. In IPv4, we had the network portion by default and the host portion by default split into 3 different classes, in which we had a class A address, which was the first 8 bits representing the network, the last 24 bits representing the host. Class B by default was 16 network, 16 host. Class C was 24 network, 8 hosts. We've already gone through that in the previous videos. Now, rather than keeping this class system, what they did in IPv6, they just set up a simple way of doing subnetting, is in the sense that they said the first 64 bits, which is basically the first 4 blocks, because each block contains 16 bits times 4 blocks gives you 64 bits, represents the network portion. So it's a flat model. It does not use the class model. The network bits is 64 bits. If you equate that into hex, it is the first 16 bits. And the last portion, the host portion, is another 64 bits. That gives you unlimited number of addresses available for assigning to hosts. You're never going to have a network that big. All right? So we'll go into more details about how we can do subnetting over here as well as we go through it. For right now though, just to give you an example, the default mask over here is /64, or the first 64 bits are network, the last 64 bits are host. So this portion over here would represent your host portion. This would represent your network portion. It's a flat model. There is subnetting as well, but I will show you how subnetting differs in IPv6 versus IPv4 in a later video. For right now, just understand it. At the default stage, if I had a class A, I would have a /8 mask. Class B would have a /16 mask. Class C would have a /24 mask. In IPv6, there's no such thing. It's a default mask of /64 for all networks. Now, some of the examples of writing an A or a B or a C is over here. If you take a look at it, class A, this is an example of a class A address. How do I know it's a class A address? The first over here, first octet is between 1 through 127. It's a class A address. So if it's a class A address, the default mask is going to be /8. So 5.1.1.1, where this represents the network portion. This over here is the host portion. All right? Basic network without doing any subnetting. The second number that you see over here is a class B address. How do I know it's a class B address? Again, this number is between 128 to 191, which we've already gone through in the other videos. So for this, the first 2 are what? The network portion. The last 2 are the host portion. Actually, made a mistake over here. Let me correct that before we go on. So this portion over here in class A, this is the only network portion. This is your host portion, the bigger one. Apologize for that. Now the third one, class C. How do I know it's a class C address? The number is between 192 and 223. That's a class C address. In a class C address, my network portion now is the first 3, and the last portion is your host portion over here. And these are the default masks that I have. In an IPv6 address, though, as I said, the first 4 blocks, these guys over here represent the network portion, which equates to 64 bits. And the last 16 hex digits is the host portion, which again represents the host portion, which is the other 64 host bits. Hence the /64 representing the network bits over here. So these are the differences between IPv4 and IPv6, and we'll go into detail about how IPv6 addresses are written, but making you understand it based on your prior knowledge of how do I compare an IPv4 address to an IPv6 address. That's the purpose of this particular slide over here. Now, as I said, it's very important for you to understand how the underlying numbering system works and how does it compare to the other numbering systems, because when you break down an IPv6 IPv6 address, you need to break it down into the different other numbering systems or compare it to them. So the first thing I'm going to do is a simple one, is the comparison between a decimal to a hexadecimal number. It's a very static type of numbering system. If you want to convert a digit in from decimal to hexadecimal, it's a fixed format. As I said, a hexadecimal is 4 bits, and the bit values are 1, 2, 4, and 8. Again, the same table, you start with 1 and keep on doubling. Those are the bit values of the 4 hexadecimal digits or bits. So if you put numbers in there, the highest number that you can have is 1111 in terms of binary. So if you have that, it becomes 15 in decimal. All right? If it's 15 in decimal, how do I represent that as a hex value? Now, when I do a conversion of writing a decimal value into hex, this is a very simple formula to do that. 0 through 9, if it's a number between 0 through 9, it is written exactly the same way in decimal and hexadecimal. But as soon as you get to 10, in decimal you would write a 10, but that 10 is represented in hex with the letter A. So because you run out of digits after 9, to represent the next hex digit, the 10, which would have been 10 in decimal, is represented as an A. Similarly, B is represented as an 11, C is represented as 12, D is represented as 13, E is 14, F is 15. As I said, the highest hexadecimal digit that you can have is 15. So this is where it ends. This is an F. Why is it 15? Because as I said, the hexadecimal digit is equivalent to 4 bits. And the bit values, even if you turn all of them on, the bit value will give you a number of 15, which is this guy over here. So again, to recap over here, the hex digits that you write are going to be through 0 through 9 and A through F. And they're represented in terms of decimal like that. All right. Now the other conversion that you also need to be aware of is the binary to hexadecimal, which I alluded to briefly, but we'll go into more detail over here. Now when you do a conversion between hex and binary, you need to understand, as I said, there's 4 bits that make up a hex digit. It's 4 bits make up a hex digit, and you put the different combinations over here. You start with, let's say, 0000, which is basically a 0 in hex. And you keep on adding. Let's say you add 110, which is a 6 as an example. Then I'll go to 9, 1001, which is 9. You still write it as 9 because 0 through 9, it's the same as decimal or hex. But if I want to convert this number over here into its hex equivalent, it's 8 plus 2, which is 10. If I want to write this in my IPv6 address, I'm not going to write 10. I'm going to write the letter A. A represents the decimal equivalent of 10 and a binary equivalent of 1010, which is again equivalent to decimal of 10, and in hex I would write the same number as A. So if I had to do a triangle of any digit, let's do a couple of examples over there. Let's say I had to write the letter or the hex digit B. How would I write it? In your hex, it would be B. In decimal, B, if you guys remember, A equals 10, B equals 11. That's fixed, so you don't need to do anything special over there. Just remember them. So you start with A as 10 and keep on incrementing till F. So this automatically would have been 11. Now, if I want to convert this to, its binary equivalent, it would be basically, if you remember the 4 bit values that I have, how do I get 11? I get 11 by adding 8 plus 2 plus 1. That's 11. So 1011 would be your 11. So this number over here is the same number. This is in hex, this is in decimal, and this is in binary. Let's do another number like that. Let's say we have a hex digit of, oops, this is the same, this won't change. Let's say we have a hex digit of E. How would I write E? In hex, E is E. E over here is 14, so I would change this to 14. And if I want to get my equivalent in binary, again, I need to get the combination in my bits to get to 14. So how do I do that? 8 plus 4 is 12 plus 2 is 14, 0. So 1, 1, 1, 0 would be your, binary equivalent of the letter E. This is important because as we go into the hex value, you would need sometimes to know how to break down a hex value into its binary equivalent, because there's certain rules that apply which are based on the binary. Hopefully everybody is good with that. Let's take a look. I might have some examples for you guys over here. So 6 in hexadecimal is 6. And in binary, I would write it as 0, 1, 1, 0. Why 0, 1, 1, 0? Because my focus over here is the binary part of it. The reason it's 0, 1, 1, 0 is because of 4 plus 2 is 6. So it becomes 0, 1, 1, 0. That's what I'm writing over here. So 9 again, very simple. 9 over here in decimal is 9 over here in hex. How do I write 9? 1 over here under the 8, 1 over here under the 1. These two are 0, so 1, 0, 0, 1. Now let's get into the other stuff over here, which is dealing with this guy 11, or A is 10. I did it for each one of those digits. So 10 would be represented in hexadecimal as A. That's an automatic, that's a fixed chart. So 10 is an A. If you have 10 as an A, you need to write 10 based on these combinations. That would be 8 plus 2, which is 1, 0, 1, 0. 1, 0, 1, 0, 1 for B, which is 11. C is 12, which is 1, 1, 0, 0. D over here is 1, 1, 0, 1, which is 1, 1, 8 plus 4 plus 0 plus 1. So basically 8, 4, 12, and 1, 13, which is your D. And so on and so forth. The largest number that you could have is all the 4 binary bits turned to 1. And that's the highest number. So if you turn all the bits on, which is 8 plus 4 plus 2 plus 1, which is a 15, which equates to an F. So 1111 in binary, in that hex digit, represents an F. That's the highest number that you can have. All right. So this is some examples that you guys have for conversions between IPv4. Sorry, not IPv4. For binary to decimal, decimal to hexadecimal. Now, some of the things about IPv6 addresses, some of them we've talked about, some of them I'm going to reiterate over here and show you an example of an IPv6 address. So first thing, we know about this already. IPv6 addresses, the size is what? 128 bits in size, which I can also write as what? Which equates to how many hex digits? It equates to 32 hex digits. How do I get 32 hex digits? Each hex digit is equivalent to 4, which makes this address a 32-bit address because of 128 divided by 4. The IPv6 is written in hex format. We already established that. This is also done. Now, the other thing that we also discussed is the way you write it. You don't write it in binary, you write it in hex. And the way the format is that you write 4 hex digits, separate them with a colon. This is known as a block. And because you have 4 of those hex digits, you have a total of what? 32. 32 divided by 4, you get 8 blocks. So the total number of blocks in an IPv6 address, each block containing 4 hex digits, is going to be 8. Hopefully you guys are understanding, following along at this point. 5, this is 6. 7, and 8. Now, when you look at it, it's 32 hex digits, and as I said, each hex digit equates to 4 bits. So you have 32 of them, that gives you the 128 bits. This is done, this is done. Now, a typical example of an IPv6 address is written over here. 2000, 2000, ABCD, 9104, F12AB. So you have some digits over here. Those are hex digits. 1234, COFF, C0FF, EE11, 0091. So that's the total IPv6 address. And as we also talked about, the first 64 bits, which is the first 4 blocks over here in IPv6, it's a flat model. This represents your network portion. And this over here represents the host portion. All right, that's this bullet item over here. All right, so these are the characteristics that make up an IPv6 address. That makes for a long address. So this is like saying, if I want to ping this host, which I used to ping for connectivity purposes by using 192, let's say 5.1.199, now I need to ping this guy. I need to say ping and go through this and write this out. Becomes a cumbersome deal. DNS plays a big part over here. All right, so this is how I would ping it. But there are certain things that you can do to make it easier on yourself. Those are your shortcuts for writing the IPv6 address or configuring the IPv6 address. And that's the next thing that we're going to discuss over here. So how do I write or configure this IPv6 address? Because it's a long address. There are 3 different levels of shortcuts that you can have. The first shortcut that you can have is that if a block contains all zeros, you can write a single 0 to represent the block. Let me give you an example of that. If I had an address like this, one, two, three, 4, 5, 6, 7, 8. Let's do another one over here. We'll change this also to all zeros so that you can see more usage of it. So this is my address. This is my IPv6 address. Pretty long address compared to what we have been used to writing with IPv4. But that's the whole thing. It gives you a lot more flexibility or address space to write these addresses. So I would write it as 2000. The shortcut, the first shortcut that you can use over here is the whole block over here. Rather than writing the 4 zeros, I'm going to represent it with a single 0. The single 0 over here basically is telling the device that this block is all zeros. So you don't need to write all 4 zeros. You can write a single 0 over here. And the rest of it will remain like that. Again, another block with complete zeros. I'm going to put a 0 over here. And write it like that. So this is your first level of shortcuts that you can have. And I'm going to show you more, but this is where you start with the block. Rather than writing all zeros in a block, you write a single 0 in the block. That's the first way. All right, now that I'm done with that, let's go to the second one. The second shortcut that you can have, if you have any leading zeros in a block, you can omit the leading zeros and write the number without the leading zeros. Let me talk about what the leading zeros are versus the trailing zeros. So let's write another example for that. If I had an address like this, Again, 1, 2, 3, 4, 5, 6, 7, and 8 blocks. This is a complete IPv6 address. Now, what I mean by leading zeros in a block, if you take a look at this block over here, block number 2, you will notice that this block over here has, oops, sorry. This block over here has 2 zeros that are in front of the digits. So it's like writing a check. When you write a check and you want to write a $100 check, you don't write the $100 check like this. These 2 zeros in the front mean nothing. You could, but the banker would know, the teller would know that these 2 digits over here are meaningless. The actual digit starts over here because the leading zero, these are called the leading zeros. So every block, if it has any type of leading zeros, you don't need to write it. The system would understand the first 2 digits are missing over here because I'm just putting 2 digits over here. So if I write this number as 2000 followed by :10, :10 automatically tells it, hey, there were supposed to be 4 digits. I don't have 2 digits. They have to be leading zeros. So that's what the leading zeros, omitting of the leading zero means. I cannot omit the 3 zeros over here. These are called trailing zeros. Trailing after any digit. It's something that you need to write. It's like if I omit this, it becomes 1. So that's wrong. So 2101, I have to write like that. This one I already showed you. If it's a complete block of zeros, you can represent with a single zero. 1, 2, 3, 4 as is. 2100, I need to write 2100. These are again trailing zeros. These are zeros in the middle. And another block where I have some leading zeros. So rather than writing 0001, I can just say 1. That it tells the device that, hey, I needed 4 digits over here. I only see 1. Though what that means is that in this block, the first 3 digits are all zeros. So writing 0001 is equivalent of writing 1 inside the block. So it's within the block though. This omitting of leading zeros is within the block. Its scope is the block. All right, so that's your second shortcut mechanism that you have. If you have leading zeros in the block, you can omit the leading zeros. The third set is called a contiguous block or a double colon. What is that? Now, in a situation where you have a bunch of all zero blocks, so for example, if I had 2100 followed by ABC1 as an example, one to AB, 1211, 911A. So again, 8 blocks over here. The way I could write this or create a shortcut for it is if I have contiguous sets of zeros, over here I do, or blocks of zeros. What I can do is I can write the same number over here in a shortcut form saying 2100 ABC1 : colon, which is called a double colon, and continue on after the contiguous set of zeros. Now, how does it know how many zero blocks do you have? It knows that the total number of blocks that you have is 8. It sees on the left-hand side of the double colon, you see 2 blocks. On the right side of the colon, you see 3 blocks. So the device calculates that I need a total of 8 blocks. 3 blocks are missing because of the double colon. Those 3 missing blocks are all zeros. So if you have the double colon, it represents the missing blocks, and all these missing blocks are going to be all 0 blocks. But the thing is, you can only do this double colon once in an IPv6 address. You cannot do it twice because then it would not be able to figure out how many blocks on the left and how many blocks on the right. So you can use this once in an address. So for example, if I also had this in the address, how would I write it? So I have two blocks, 3 blocks of 0, 1 block, and let's say, hypothetically speaking, I had another 2 blocks of zeros over here. Now I need to pick and choose in terms of which block do I want to use the double colon for, because I have 2 sets of double colons that I could use because I have contiguous blocks. So what I would do in this case, pick the one that I can eliminate the bigger block. So this double colon over here would eliminate the 3 blocks. I would write 1, 2, AB, but I cannot do another double colon over here, so I would represent the first block as 0, second block as 0. So now again, it knows that I have 5 blocks represented, 2 on the left of the double colon, 3 on the right of the double colon. That again puts me with 3 missing blocks, which is going to be I can only do it once inside an IPv6 address. So this is a all 0 block by itself. This is the double colon, which is all the missing blocks are zeros. So this again only once in an IPv6 address. So that's what this third shortcut is all about. If you have a contiguous block of zeros, you can represent them by using a double colon. You can use the double colon only once in an IPv6 address. I think that's what the examples would clarify for you. Shortcuts for writing IPv6 addresses, some other examples for each one of them. If a block has all zeros, you can write it as a single block. So if I have a normal IPv6 address like 2111, a whole bunch of, or an all 0 block, AC00, I cannot do anything with this. 0000, 0123, 0000, 1000, 0008. So first thing that I did over here, I eliminated what? The 4 blocks and put a single digit over here. AC00 as is. These 4 are represented by a single one. 1, 2, 3, 1. You also notice that I eliminated the leading 0 over here, becomes 1, 2, 3. All 0 block. 1000 as is. AB, I eliminated the leading zeros. That's a shortcut IPv6 address to represent this. As you can see, there's a sizable difference in the two addresses, sorry. The second one, you have leading zeros in a block, you can omit them. So another example for that, keeping more of a focus on that, 2111 as is. 0005 is written as a 5. AC00 with the trailing zeros, leave it as is. 00AA is AA. 123, 0123 is 123 only. Complete block of 0, that's here. 0000, 1000, AB, eliminate the leading zeros. So that's another example of that. I think done enough examples of that. And the last one, if you have a contiguous block of zeros, you can represent by using a double colon. 2111, 1, 2, 3, 4, 5 blocks, and then I have 1000 AB. So actually in this example, I could have written this. If I really want a full shortcut, I could have written it like this. 2111 colon colon, a set of zeros is coming up. How many? I don't know yet. And I could write this as AB because I could eliminate the leading zeros on this block as well. So I have a block 1, 2, and 3. So I have 3 blocks. So the double colon over here represents 5 missing blocks. And the device would calculate that automatically for you guys. All right. So this makes it more manageable to write rather than a big address. Especially on the host portion, I would do that a lot to write the IPv6 addresses. All right. So now to recap the lecture over here, let's take a look at the review questions. What is the size of an IPv6 address? Very simple. 128 bits, which I can also write as 32 hex digits. What is the default mask of an IPv6 address? Oops, sorry. 64 bits. Write the following hexadecimal for the following binary numbers. 1101, so 1101, 8 plus 4 plus 1. So 8 plus 4 is 12, plus 1 is 13. So if you do that table over here, A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, and F equals 15. You have that table in front of you, or you have it memorized in your mind. So if you see 8 plus 4 plus 1, which is 13, you would write that as a D. So the next one, 0010. So 0010 is basically, I'll keep this table here, handy. 0010 is a 2. 2 is represented as a 2. This number, 1001, these are easy because you don't need to use this table for anything up until 9. So 1001, 8 plus 1 is 9, so you write it as 9. 1011, now this is where you would need some conversion. 1011, which is 8 plus 2, which is 10, plus 1 is 11, which is A, B. 0011, 0011 is a 3. I'll write it as a 3. 1001, which I've already done over here, as a 9. 1019, 1010. 1010 is a 10, which is an A. All right. So following hexadecimal number for the binary ones is done. The next one, write the following decimal equivalents for the hex digits. That's simple. If I have this table up front, A equals 10, B is 11, D over here is 13, and this is 15. What is the shortcut notation for this guy? The shortest shortcut that you can write, 2000 will be as is, 0090 will be 90, 0ABC will be ABC, ABC 0 is still the same, this is a trailing 0, AB00 is still the same, 0001 is 1, 0909 is 909, eliminating that leading 0, and all zeros is a 0. Okay, for this guy, 2000 colon colon, because I have 3 contiguous blocks of zeros, then AB 00 colon 1 colon 909 colon 0. So that would be your equivalent for this particular address. All right. So hopefully you have a better understanding of what an IPv6 address looks like. For example, if you take a look at this address over here, what do you guys see? You see this as the network portion and this as the host portion. This is the default way that IPv6 address looks at it. You looked at the binary to hex conversion, decimal to hex conversion, and then the shortcuts. Hope you guys enjoyed it. Please follow on the next video, which goes into the different type of IPv6 addresses that you have, like public, private. See you guys in that video.